Hello students, welcome back. So now we are going to add some more functionalities into a simple register. We are going to design a register with additional clear signal. So in this video, we are going to talk about additional features that can be added to a register. We are going to talk about the clear function, combining the load and clear features together, and we are going to design a negative or positive edge triggered register with these features. So let us get started. Depending on the specific cases, sometimes the user can ask us that I want some additional features in my design. So we can augment, we can enhance the existing designs. The basic functionalities can remain almost the same, but the additional features can override those functionalities. These features may not be required in every register that we design, but these are all user specific. We have to work on the priority. That means which feature will have the higher priority and which one will have a lower priority. Let us talk about the clear function or the feature that we have in a register. Sometimes we need to reset or clear the content of the register. One simple way is you can set the load signal to 1 and load 4 zeros or 8 zeros depending on the size of your register. But we suggest not doing it. We say instead of that, provide one additional control signal, and whenever that signal is assigned as 1 or 0, we can set every value to 0. So this is what the clear signal is. Let us talk about the 1-bit design. Here we have the circuit diagram. So what are we saying? We have now two signals. One is load and one is clear. They are going to decide the operation. If clear is 1, then the value of load is not considered at all and output will be 0. Now, if the value of clear is 0, then we can talk about load. And in that case, if load is 0, we are going to hold our data, and if load is 1, we are going to load a new value from D0 into our flip-flop. And then we can extend the same logic to more number of bits. Now, let us talk about the practical aspect. The D flip-flop that we had will not work. We need to redesign. We need to add that clear input as well in the D flip-flop. We can also design the same using if-else conditions. So, using if-else condition, you can set the priorities very clearly. Now, let us design it in Verilog. So here we have the code. I have input which is 4-bit D. Then I have my clock signal, load and clear. These are 3 input signals. My output is a 4-bit number which is 320 and the name is Q. I define Q as a register and then I say always at the rate positive edge of the clock. You can write it negative edge as well. Then we begin and here we end it. Everything is written between this begin and end. Now we say if clear is equal to 1, assign Q is equal to 4-bit value 0000. Else, in that case, that means if clear is equal to 0, then we say begin. This is completely inside one else condition. Okay, this is the condition which is separate. We say if load is equal to 0, that means we are holding, assign Q is equal to Q. Else, that means we are loading a new value. In that case, Q is given as D. Now for this, I have written a test bench as well. In the test bench, we have declared the output as wire and inputs as registers. There is one register which is 4-bit in length, and there are 3 registers which are single bit. Then I instantiate my register 4-bit with clear. This is the module that I had earlier. I set everything in the order, and then I say always with a delay of 20 nanosecond, clock becomes invert of clock. That means we are generating the positive and negative values, that means 0 and 1 after every 20 nanosecond. So 40 nanosecond is the time period. Then we say initial, begin and end. First of all, I allocate the value of 1 to clock. Now clock is set as 1, and after every 20 nanosecond it will flip. At a delay of 10 nanosecond, I set clear to 1. After 100 nanosecond, I say load is 1, and I am trying to load binary number 0010, which is 2. After 50 nanosecond, I set clear to 0. That means anything before this will not be considered because clear is 1. And when I set clear to 0, then this value can be loaded, and after that I am setting load also as 0. So these are all the combinations that I have given, and now we have a look at the waveform that is generated. So initially at 0, clock is set, clock is always running. There is no value assigned to D or anything, so the Q is undefined. Now what I do, at this edge we detect that clear is 1. Whenever clear is 1, the value of output will be 0. At this edge clear is 1, it remains 0. At this edge clear is 1, it remains 0. At this rising edge clear is 0. Then we say okay, what about load? Load is 1, so we are going to load the value of D, and the value of D is 2, so 2 goes here. At this edge load is still 1, and we are loading 2 again. At this edge load is 1, we are loading 2. At this edge, now what we see, that we have set load as 0. So now we are going to take the new values and load them accordingly, and we can continue for whatever amount of time we want. So students, now we know about a basic register and slight variations that we can do. There are a lot of different other types of registers that are there in the literature. We are going to talk about them in our next video. Keep learning. Thank you.